Everyone, welcome back to discussion 14. Let's get right into it. Problem 75 on page 246. At 220 meters, the bungee jump at the Versasca Dam in Locarno, Switzerland, is one of the highest jumps on record. It says the length of the elastic cord can be modeled as having negligible mass and obeying Hooke's law. It has to be precisely tailored to each jumper because the margin of error at the bottom of the dam is less than 10 meters. Kristen prepares for her jump by first hanging at a rest from a 10-meter length of the cord and is observed to stretch the rope a total of 12.5 meters. And then we're asked to find what is the length of the cord Kristen should use for the jump to be exactly 220 meters. And then we need to know the maximum acceleration that she's going to experience. Okay. On a little bit here. Here is our bungee cable and our mass. This is the top position is going to be y equals 0 meters, and this is y equals 220 meters. And we can show the total length of this thing is going to be 220 meters, right? So that's kind of what we have over here. But let's just say that this is the jump, just to kind of draw it out. So this is total h. This over here is going to be L. So then we call this version here, this is h minus L, right? So let's start by kind of modeling also our energies. At the top of the jump, it's going to be mgh, of course. And then at the bottom, there's not going to be any gravitational potential at the bottom here. It's going to only be the potential of the displaced spring, right? This rope is modeled as a spring. So this thing comes down here. This is going to be your equilibrium position. As you jump down, it's going to extend all the way to the bottom. Gravitational potential goes away, and we only have the displacement of the spring from equilibrium. Okay, so that gives us half kx squared. Or rather, in this case, it's actually h minus L squared. Okay, so we're given some information that we can use right away. We're told that, let's write it over here. We're told, using Hooke's law, kx is equal to, what was it? It was mg, right? Because that's going to be well, I guess I should be more clear. Let me rewrite this. Let's go with, so we're gonna sum up the forces. If we put the mass, we hang the mass into equilibrium, that's what we're told happens, right? So we're in equilibrium, and we have Hooke's law for the spring, right? And we also have an opposing force, mg. So in equilibrium, we have kx is equal to mg. So if this thing is just hanging here, right, we have some with a mass on it, with a mass on it, so that this is displaced a little bit, and we're told this is 2.5 meters. So this comes down, and we have a balance of weight force and the spring force, okay? And then it's motionless. So we can use that information here to set these equal. So now we have k is equal to mg over the displacement was 2.5 meters, right? That's a good starting point. So now we want to know what is the length of the rope, and we can find a relationship. So this k. So now we want to know what is the total length of this cable that we need. So we can use what's similar to a proportion. So we have k times L. We'll call this L, big L, right? And that's going to be the same as saying, since we're using the same type of cable, k prime times the length of the other rope, which was 10, right? We were told the original rope for which we found this was 10 meters. So, okay, that gives us k equals k prime times 10 over L, which is equal to mg over L, 10 over 2.5, right? Because I just plugged this in here. Okay, so that gives me 4 mg over L. All right, and so this is the spring constant now for the full length of the rope, right? We used the information that was given. We used the forces in equilibrium, and then we found a relationship for the original spring constant, right? This was the displacement from equilibrium. Then we took that and we set it equal to the full length of the rope times the spring constant. Solved for the full spring constant by plugging in, and now this is what we're left with. So now we can use conservation of energy from here to find this length L. Okay, so we're going to have mgh is equal to half k h minus L squared. All right, that's going to give us mgh is equal to half 4 mg over L h squared plus L squared minus 2hl. Okay, that's going to equal to mg right. Okay, just doing a little bit of solving here. Get rid of this. Well, I'll write this down, mgh. So these actually go away, right? Then we're left with height is, by the way, is 200. This h, total h, is 220 meters. That's what we're told. So this, take this to the other side, or we can say divide both sides by 2, right? And that gives us 110 meters equals, say, 220 squared 1 over L plus L minus 2h. Or an easier way to do this would actually be to just say, let's do it this way, 110 times L is equal to 220 squared plus, what do we do, L squared minus 2hl, right? Let me take this at 0, L squared minus 2hl, which is actually going to be, this is 440 because the h was 220, 440L minus 110L plus 220 squared. So that leaves us with a quadratic equation that we can actually solve. Minus 550L plus 220 squared. Okay. Just writing out the quadratic form. This is just going to be 550 squared minus 4 times 220 squared. Alright, so this gives us a value L. So just plug this into the calculator, and we get two values because we have a plus and a minus, right? Plus and minus. So you have to do both of those. So we get 440, and then we also get 110. So, well, we know that 440 isn't a reasonable value because we can only go to 220 meters. I mean, the whole length of the gorge or the valley is 220 meters. So 440 meters is obviously too long. If you give a 440 meter rope here, this person's just going to fall and slam into the ground. So we need something less. So 110 meters is actually quite reasonable. So let's say this is 110 meters, and then they jump and then they have almost twice the length to go almost to the bottom. So that's what we're saying. So we're saying that the length of the rope is 110 meters. Okay, so well anyway, we can sum up some forces to get to the maximum acceleration, right? So we know that the sum of forces is equal to m net acceleration. That's going to be equal to k delta x minus mg. Okay, so let's see, what do we get here? So let's take a net is equal to k delta x over m minus g. Okay, recall that this delta x is going to be how far we're displaced from the equilibrium. So it's going to be this value anywhere in here, so it would be h minus L. All right, and we have a value for our L. So now we're looking at, and what was K? K was 4mg over L. 4mg over L times h minus L. Now we're saying this is over m minus g. Say we're getting somewhere. So now these cancel, right? So now we have 4 times g. We'll call this 9.81 meters per second squared. This is going to be 110 meters. Okay, this is going to be 220 minus 110 minus 9.81 meters per second squared, right? This is in meters. Yeah, meters. Okay. Plug that into a calculator. This gives you a value of 29.43 meters per second squared, or about 3g. Or about 3g. So that seems quite reasonable. I believe it's most bungee jumps. I was looking at this up, and most bungee jumps don't go over like 5g. And so the fact that this one is at 3g seems perfectly within reason, and the fact that the cable length is 110 meters. I would say that this seems like an answer. Okay, next problem, number 12 on page 275. We're given a force. An object is subject to a force such that 10,125 joules of work is performed on the object. We're told it travels 25 meters in the positive x direction. What must be the displacement of the object in the y direction? Okay, so here let's just write out what we have, right? That's usually the best thing to do first. 512I minus 134J. Okay, we're told that work is equal to 10,125 joules. And we're told that the displacement in the x direction is equal to 25 meters. Okay, let's recall that work is equal to F dot dr. In this case, we're just going to use deltas. Delta R. Okay, so we have a dot product. So then we're given work, so let's do this. 125 is equal to our force vector dotted with let's see, we have 25 displaced in the I direction, and then we're looking for the displacement, let's say delta y, in the j hat direction. So that's how we would set it up. We're given work, we're given the displacement in x, we're given a force. The only thing we don't know is displacement in y. Okay, and so we just have to take the dot product, which is multiply I hat by I hat, and then j hat by j hat. Okay, so that gives us 512 times 25, and it's useful to know that I dot I is equal to J dot J is equal to 1. Okay, so when you're multiplying unit vectors by itself, it just comes out to 1. All right, so where were we? Let's see. And then we had minus 134 times delta y. It's equal to 125 joules. Okay, and we just solve. That's all we got to do. So 10,125 joules minus 512 times 25. And we take this negative to the other side. So we're actually going to have minus and then plus here, and then we multiply this by 1 over 134, and that equals delta y. So then I plug all of this into the calculator, and I get a value of 19.96 meters. So that is the displacement in the y direction. So just recapping real quick, this is all that we're given. We recall that work is equal to F dot dr. Here's your work. You're given this information. You're given your force vector. You're told that the displacement in x is 25, and you're solving for the displacement in y. So you take the dot product, you come out with this, and you solve for y. Okay. Okay, for number 15, we're given two vectors. A cos. Well, if you just I'll just write them down real quick. So we're given these two vectors. Okay, a cos 15 I hat, a sine 15 j hat, and the same thing for b cos 15 I hat plus b sine 15 j hat. We're asked to find the angle between these two vectors. So if I remember correctly, this is the chapter where they're introducing a dot product. So for anyone who hasn't seen that before, it's pretty straightforward. It's kind of just the thing I was just showing, where we take the value in the same direction, right? So this is both I hats, so we multiply the I hats together, we multiply the j hats together. So we do the same thing here, but we also have this cool identity that gives us an easy way to find the angle. This is in your book. I don't know what page, but it's in chapter 9, so you can find it. I'm pretty sure it's actually probably right here. Yeah, page 274. It gives you this. It explains how to do a dot product. And I'm sure it does in other pages as well. Anyway, the point is, we can take this, so we can just take the dot product directly, right? So then we get a. So let's just set this up. I'm just going to take the dot product of the vectors that we're given. We get a b cosine squared 15, because they're both 15, right? This is 15 degrees, this is cosine 15 degrees. So those are the same, and we're just multiplying the I hats together. Next we go to the j hats, and then we get plus a b sine squared 15 degrees, right? That's going to equal magnitude b cosine of the angle, right? I used theta before, so let's stay consistent. Okay, so notice here that we have cosine squared plus sine squared 15, and the coefficients are the same, so this actually just gives us ab, right? And then this is going to be magnitude a times magnitude b times cosine of the angle. So we can find the magnitudes of these vectors by simply taking, so let's find the magnitude by squaring each component and taking the square root, right? So then we have a squared cosine squared 15 plus b squared sine squared 15. Oops, sorry, my fault. That's a, not b, because I'm taking the magnitude of just the a vector, right? So I square each component. This is squared plus this squared under the square root. That gives me this. And again, this is going to equal 1. Now I just have the square root of a, and that gives me just a value of a. The same thing is going to happen for B. I don't need to go through all of that, but you can do it yourself, and I encourage you to if you're a little confused about this. So square each component, square this, plus square this under a square root, and you'll end up with B. So the magnitude of B is equal to the magnitude of B. If we were given some values for plugging in here into these vectors, it would come out differently. But right now, it's a pretty straightforward problem. So now we have, what did we have? We had AB is equal to magnitude A times magnitude B, cosine of the angle. And, well, these are going to cancel because these are equal, right? So that means that 1 is equal to cosine theta, right? Well, we know that that's going to be, theta is going to be 0 degrees between the two vectors. And that makes sense because, well, these vectors are in the same space, right? These are in the same plane. They're both pointing along 15 degrees. So what we have essentially, I think it actually asks, yeah, sketch the vectors on an XY coordinate system. So we can do that. So let's, because I was just about to do that anyway. So here we go. Sketch this. This is Y. This is X. Right? And so we had, it was 15 degrees, let's say 45, 0, 30. Let's go here. We don't know what the magnitudes are numerically, but we can kind of come up with some idea. Let's just say A is larger than B, just for this sketch, okay? So they're both at 15 degrees. Let's just call this 15 degrees, just like we're given. Now, B is going to go here. So there's nothing really to change. So there's no angle between them. Because if there was an angle between them, instead of B being right here, it would actually be like up here or, I don't know, over here or something. And then we could actually find an angle between the two vectors. But that's not the case. We're told that they're exactly in the same direction. They just have different magnitudes. So here, here are your components for B. And then you could say that your components for A are over here. But still, none of this changes the fact that they point in the same direction and that the angle between them is 0. So that's the answer. So we're given that there's a block and we've compressed the block against a spring 30 centimeters, right? This thing is going to take off. So it's going to have some velocity here. Then it's going to slide down this hill, which is at a 40-degree angle from the horizontal. It's going to slide down the hill, and then it's going to continue sliding this direction for some distance. We don't know what. And that's what we want to determine, is how far is it going to slide over here. Okay, the very first question is conceptual. It says, what do you include in the system? Explain your choice. Well, I would include pretty much everything you see here, right? We have a block, we have a spring, we have a track, and we need to include the Earth because we're going to have some gravitational potential as well. So that's what I would include. So to write that down, I would include the spring, block, what did I say? Track. We're going to need the track, we're going to need the Earth. Right. So that's what I would include. Next part, calculate D. All right. So this chapter is dealing with the work energy theorem. And given that we're going to have some potential energy in the spring, we're going to have potential energy up here from gravitation, we're going to have kinetic energy from this block in motion, right? We're also going to have, since we're told that there's some friction along the horizontal parts, just double checking, yeah, there's friction along the horizontal parts of the track. That means that there's going to be a dissipative force. In other words, there's some work being done. And so we can use our work energy theorem. So let's recall that work is equal to the change in the energy, right? And so what we can do is we can take this plus the initial energy is equal to the change in the internal energy plus the final energy. This is all directly from the book also, just so you know. Okay, and then so now we can break these energy equations down, right? We're going to have a kinetic initial. We're going to have a potential initial. Then we have the work being done. So this is just the general theorem that I'm laying out right now. I'm not actually quite to solving the problem yet, okay? And then, okay, so now we're going to have pretty much the kinetic energy of the block is just one thing, but then we also have two types of potential. We have potential for the spring and potential for the gravitation, right? So that means that we have KE initial plus, we'll just call this gravitational initial potential, and then we have elastic initial potential plus work is equal to kinetic energy final plus possible gravitational potential final, possible elastic potential final, plus this change in internal energy, we're told also in the book. I mean, since this is some sort of work being done, it's actually the frictional force times the distance that is traveled. That gives you a change in energy. So that's going to be the frictional force times the distance. We'll call it D, because we're going to end up using this down here. Okay, so that's the general theorem. So all I did was I just kind of went through the steps, right? This is the beginning of the theorem, and then you can add in your energies, and then you break apart your energy, and then you break it apart even more depending on what's in your system. And we have a few things going on in this problem. I mean, there's a spring, and there's gravitation, and there's friction, and this is all sliding down a hill, and so yeah, there's quite a bit going on. So it's nice to just kind of lay everything out and see what you're going to end up with. Well, we have three paths. What I mean is, let's just do this, right? We'll call it A equals EF plus the change in internal energy, right? Okay. So for the first part of this problem, we don't actually, so let's say in the initial stage, so actually what I said a minute ago is not, I want to do it this way. So this is going to be our initial energy, right? We have the spring potential. That's important. We need to include that. So we're going to have a spring potential energy. Once that releases, the block is going to have some kinetic energy over here. It's also going to be sliding across this horizontal surface, and there's friction. So the final has kinetic energy. It's going to have potential energy sitting up here, at this height above the horizontal, and it's also going to be doing, there's going to be some change, so there's going to be some work involved. Okay, so let's write that out. So EIA, we'll call it. There's no work being done in the first part of the problem. There is, however, some in the next part of the problem, so we leave that in there. Okay, so we're going to want to know what is the energy here so that we can get to this point here. So this will be our initial, so the final energy for this first part. So here we have initial, and this is going to be final over here. So this final energy is going to be the initial energy for the next part. So we want to solve for that. So we need to know what is the final energy going to be. So it's going to be EIA minus the change in internal energy. Okay, cool. So that gives us something that we can work with. So now we have, and this is going to be the frictional force times the distance. I'm just using S for now. That's kind of what they use in the book as a default. This is minus mu k. Remember that the frictional force is the coefficient of friction times the normal force. Okay, and also recall that this is 30 centimeters. So the distance here is 30 centimeters that it's going to travel with friction. Also, if we note here that the normal force is just going to be equal to mg, right? There's no angle here. This is just a horizontal platform. So this is mg. This is your negative weight force, and this is your positive normal force, so that's just going to equal mg in this situation. Okay, so now we've got EIA minus mu k mg times 30 centimeters, so this is times 0.3, right? Okay, now what is EIA? What is the initial energy of the system? Well, we have the spring potential, right? And that's going to be half kx squared, and this x is, well, it's 30 centimeters, so that's 0.3 squared, right? We have also, if we look at the diagram, this thing here is up a distance. That distance is going to be r sine 40, where r, it happens to be 50 centimeters, right? So this is going to be 0.5 sine 40 equals this distance here, right? And this was our spring potential, half k 0.3 squared, right? So let's include that. Also recall, I don't know if this is clear, but we're told that the gravitational potential, or a change in the potential, is path independent, right? So it doesn't matter how this thing travels down here or how it gets here, but the overall change in the potential is just going to be mgh. So we have the mass times gravity times h, which was 0.5 sine 40, right? Minus mu k mg times 0.3. Okay, all of that is your value for the final energy of this setup. So we have our initial energy here with the spring potential, we have gravitational potential, and we have, right, so those were our initial, this was the initial, and then we had the work being done as it travels, right? So once again, just to be clear, initial energy is, in fact, the potential of gravitation and the potential of the spring. The block is this height above the horizontal down here, so this is mgh, and we have the spring potential here, okay? It's going to travel, and it has this dissipative force going along the surface. The reason I decided not to include the kinetic energy term half mv squared in this is just because I'm just going to take this as a numerical value, because we can actually solve for that since we're given everything that we need, and that'll be a nice starting point for the next part where it's going down the ramp. So I'm going to plug this into the calculator, and I get a value of 2.932. Okay, I just wrote everything down. I paused it and wrote everything down, and then plugged it in, and that's what I get. So that's going to be in joules. And so that's going to be how much energy is stored in the block at this point here, like right at the top of the ramp. So here, let's use a different color. We use blue a lot. Let's go with red. So here, this block has energy 2.932 joules stored in it, just right here. And it's traveling, right? But this is the total energy. So we're going to use that. This is the initial energy now. We're going to use that to find the distance. Okay. Okay, so now I want to point something else out before we move on, because we wanted to consider three paths, right? So we wanted to consider initial and final energy here, which is what we just did. Then we want to consider initial and final energy here, right? We're told, however, that there is no friction on this ramp. So there's no dissipative forces, there's no work being done. So pretty much we're left with initial energy is going to equal the final energy in this case, right? So we have energy stored as this thing is traveling along, okay? There is some potential energy here, but that's not, we don't really need to break that all apart. We know how much total energy there is. which is, what was it? It was 2.932 joules, and that's going to be exactly the same as down here. So to make it more clear, we'll call this part, we'll call this B, we'll call this C, right? So energy at B is 2.932 joules, energy at C is 2.932 joules, because there's no work being done, there's no energy being exchanged with outside forces. So it's exactly the same. So now, that was easy. Now we can use this energy that we know initially is 2.932 joules, and this thing is going to travel along a friction coefficient, and then it's going to come to a stop. So we can use that information to find the distance. So we will say EIC plus, let's call it initial work. There is no initial work, but I'm just going to write it down. E final C plus the change in the internal energy, which we know there is a frictional force, so that's going to be mu k Fn dot S equals, let's make sure I got this. Right. So, where was I here? Mu k mg, it's actually negative, by the way, dot S, and S is what we're solving for. We know this is 2.932 joules, right, over here. This is the initial energy that we started with because of all the reasons I just said. Okay, so now we have some potential, maybe? Well, let's look at our diagram again. The block has come all the way down. There's no gravitational potential here. And we're talking about the final, right? So this travels along here. There's no gravitational potential here. There's no velocity because we're talking about at the point that this thing stops, right? So there's no kinetic energy term and there's no potential term. So we'll just do this, right? These are both equal to 0. These go to 0 because we're talking about the moment that this thing goes to a rest. So now all we really have to do is solve. We know all of these values. So now we have 2.932 joules over m g mu k is equal to S. Then we plug it into a calculator. And we get, that's actually not negative, now that I recall. The work energy theorem actually gives this to you in a positive value. Okay, so this is going to be, I just plugged this in, 1.313 meters. That's the distance. So this is actually, we'll call this D, right? S is equal to D. Anyway, this is your answer. Okay, so problem 51. It's exactly the same, but now we have friction on the ramp. So we already went through all the work to figure out what is the initial and final energy for the first part of the trip, right? So we don't need to do that. So we know that the energy is going to be 2.932 joules at the top of the ramp as the thing is moving. Okay, I'm going to take this diagram here. Because I want to use it. Let's get rid of some of this extra stuff. We know that's 50 centimeters, we don't need that there. We know that's 30 centimeters, we don't need that there. We don't need that. We don't need this. We don't really need this, that's just extra. We know we want to find the distance. I'll leave that there, that's fine. Okay, so we'll call this B, right? This is energy B. We know that that's 2.932 joules. So now we want this to be equal to C. But using our work energy theorem, we know there's friction on the ramp, so we have to use this theorem, right? So now we set this up this way. 2.932 joules is equal to E, the energy at C, plus the change in the internal energy along the path. Okay, so that's going to be Fk, frictional force times the distance. Well, we want energy C. We know what this is going to be. We want energy at C, so let's do this. So 2.932 2.932 minus, we'll call this mu k, and then we want this to be Fn dot S. Okay? That's going to be equal to EC. So again, EC is equal to EB minus the frictional force dot S. But now we need to find the normal force, right? Because the frictional force is expressed in terms of the normal force. Well, let's recall, what is the normal force going to be for a block on an incline, right? To do this real quick, hopefully. Here we go. So now we have okay, that looks just bad. So now we have an angle theta. We have a block on the incline. We have a normal force. We want to know what that is. There's a weight force, right, that pulls down that way. The y component of the weight force cancels with the normal force. So it's actually opposite of the normal force. Remember that. So that means that the weight force and the normal force are related by opposites, right? So it's actually going to be, so Fn is actually it's mg cosine theta, right? Great, that helps us. So now we can use that. So now we have EC is equal to 2.932 joules. I'll just call it 2.93. I don't need to write the extra 2 every time. Minus, what is it? It's frictional coefficient times mg cosine, and then the angle was 40 degrees. Right? Times the distance, which is, we're told this is 50 centimeters along this ramp, so that's 0.5 meters. Okay, so now we plug that in. Plug that in, I get 2.075 joules, or about 2.08 joules. So that's the energy at C. So notice this. Okay, this is kind of cool. So the energy at B was 2.932 joules. Remember, we went through all that trouble to find that in the other problem, right? That was like the whole first thing we did in the other problem. We found that it was 2.9, almost 3 joules. So now, as this thing has traveled down the ramp, we've lost quite a bit of energy. We've lost almost an entire joule, right? So as this thing slid down, we lost almost 1 joule, which is pretty interesting. Okay, so next we need to find, we still want to find how far is it going, so we want to find D. We want to find this value here, D. That's what we want. So we know what C is. We can use the same thing that we did last time, where we just set the value of C equal to the final energy, right? So now we have EC is equal to, we'll just call this ED. We know that there's nothing here, right? Or we can say EC final, that's fine. Plus, what was it? The change in internal energy, because there is friction along this path. So what we get is 2.08 is equal to, remember, we're looking at this block where it comes to a rest, right? So there's 0, I'll just write it out more explicitly. The change in work is equal to kinetic energy plus the potential energy plus the change in the internal or the thermal energy. We can also call it that. There's no kinetic energy when the thing comes to a rest. There's no gravitational potential when it's at the very bottom of the track. There's no work, extra work being done. We've already calculated all of that. So now all we have left is 2.08 is equal to mu k Fn times the distance, right? Distance traveled. And in this case, the normal force is just mg. So again, just do the same thing that we did last time. Here's the frictional coefficient. Mg equals, what does that equal? I'll plug that in. And the distance traveled is going to be 0.932 1993, or about 0.932 meters. And what was the other distance that we traveled? So here, let's do this. Equals d. This is our answer. What was the other one that we had? 1.313 meters was the original one. So without friction on the ramp, so with just friction here and here, no friction here, we traveled 1.3 meters over here. So once I hit this, we traveled 1.3 meters. So 1.3. Okay, with friction along the ramp, we had some resistance the whole time. The whole time we had resistance, and then we only went less than a meter. So that's actually pretty cool, and it makes sense. All right, thanks.